In today's video, I'm going to be going through an introduction of sorts to the halogenoalkane functional group. Now, in the last video, which was the third episode of the organic chemistry series, I suppose, I talked about how you can produce halogenoalkanes from alkanes by adding halogens. Seems pretty simple, but halogenoalkanes, they're a relatively normal functional group. They're not anything particularly special. You probably would have heard of things such as chlorine and fluorine and maybe bromine and iodine before, even if you are particularly new to organic chemistry in a sense of the imagination. But yeah, halogenoalkanes, they're a functional group and a homologous series which contain halogens. If you don't know what halogens are, they are in group 7 of the periodic table. If you pull up an image of the periodic table on your computer, if you look at the very far right of the periodic table, it's the row just in from the final row. There you'll find fluorine, chlorine, bromine, iodine, and then there's some other sort of bigger, more irrelevant chemicals down the bottom. Its general formula is CnH2n plus 1x. X represents any of the 4 halogens that you can find in organic chemistry, and as you'll see, these 4 halogens here are the ones that are commonly found in organic chemistry, and I've spoken about this before. The prefixes, however, for these functional groups are fluoro, chloro, bromo, and iodo. Now, these molecules here that you'll see, it's not just a chlorine with a weird line attached to it. This is actually an organic molecule. As I've spoken about with skeletal formulas before, each end or divot to a line is a carbon. So this would be a carbon and this would be a carbon. This carbon's saturated with 3 hydrogens. This one is saturated with 2. Same with all of these things at the ends. This would be fluoroethane because ethane means 2 carbons. This would be chloroethane, bromoethane, and iodoethane. That's how you use these prefixes. Now, the reason these halogenoalkanes are known as a functional group is because their presence in a molecule alters its potential chemical reactions, and that means that it has some interesting chemistry and it needs to be known as a functional group because of that. Now, I guess some facts about the halogenoalkanes. You've still got this here on the right hand side. The CX bonds, X representing all of these halogens, are all polar, and this is because halogens have a greater electronegativity compared to carbon. And you are probably looking at me like, what the heck does that even mean? What does polar mean in this context? What does electronegativity, what now even mean? And if I use this image to sort of explain it, if you imagine a covalent bond being a single pair of electrons, this hydrogen is sharing an electron with bromine, and this bromine is contributing this electron. Each atom in a bond contributes 1 electron in a simple covalent bond. Now, electronegativity is a property of each element, determines its ability to pull both the electrons in a covalent bond towards it. As you'll see here with the hydrogen and the bromine clearly has a higher electronegativity than the hydrogen because it's pulling these electrons that I've added in subtly closer, and that is represented by this delta negative symbol and delta positive symbol. Because this hydrogen is now completely electron deficient, it's going to be slightly positive because it's still got a proton in its nucleus that's keeping it positive. This bromine has many more protons in its nucleus, and that's the reason that it's able to attract this electron pair so well. But hydrogen only has 1, so it doesn't actually have that strong of a pull. Now, because of the fact that this end of the molecule is slightly negative and this end is slightly positive, you can imagine that will lead to some interesting chemistry, right? As I say, this gives them special chemical characteristics. If this end's negative, it's going to be attracted to more positive things, and if this end's positive, it's going to be attracted to more negative things. It's not non-polar and therefore neutral, and so it wants to balance out the charges that it's sort of got in this covalent bond by floating around, and eventually it'll find something that's slightly positive or completely positive, and it will try to bond to it. But before I get onto the reactions of halogenoalkanes, I'm not going to talk about that in this video. I'm going to talk about that in another video because there is plenty to talk about with the reaction mechanisms that you will find with halogenoalkanes. A little fact, I suppose. These halogenoalkanes, all of these, have to be stored in tinted glass bottles, or they risk degradation by light. This is because covalent bonds involving halogens often split under ultraviolet waves, which will produce free radicals and give rise to a lot of unwanted products. This is not exactly a halogenoalkane, this molecule here. This is just an acid because this isn't the carbon rather than the hydrogen. If you can imagine here with this bromoethane, this bromine is connected to a carbon in this bond rather than a hydrogen. Now, with the halogenoalkanes, one being a homologous series and a functional group in and of itself, the fluoroalkane series, going from fluoromethane all the way up to fluorodecane, that's going to have its own interesting trends. But also the trends of fluoromethane to chloromethane to bromomethane to iodomethane, that also has interesting trends. And that's unlike other functional groups you get, like aldehydes or ketones. There's not 4 different types of those things. And it's just these 4 halogenoalkanes. It's the separation between the two, and there are many differences between all 4 of these things. So firstly, the reactivity of the halogenoalkanes increases as you go down the group. So fluoroethane is the least reactive, chloroethane is getting slightly more reactive, and then iodoethane is the most reactive. However, the polarity decreases as you go down. This CF bond is actually incredibly polar because fluorine has the highest electronegativity you possibly can, and carbon has the same electronegativity the whole way through. So this is going to be very delta negative. However, as you now know, that does not mean that this bond is any more reactive than any of the other ones. It's actually the one of the strongest bonds you can find in organic chemistry, and that's just an interesting fact, I suppose, about the CF bond specifically. But this bond is strongest. This bond is slightly less strong even further, and the ICI bond is the weakest bond. It has the weakest bond enthalpy. It takes the least energy to break and split the electrons, either homolytically, where they go to one atom, or heterolytically, where each electron in the pair goes to an individual atom. In terms of the physical properties of these halogenoalkanes, you'll notice, maybe if I use as an example, the fluoroalkane series. The fluoroalkane series, fluoromethane is going to have the lowest boiling point, and then as you go higher and higher and higher, it's going to have an increasingly higher boiling point because the molecule is getting heavier. When molecules get heavier, they somehow, by, I guess, some chemical phenomenon that I'm going to explain, means that they have higher boiling points. And if a molecule has a higher boiling point, it takes more energy to convert it from a liquid to a gas. So there must be something holding these molecules in the liquid together. Even though they're individual molecules, you wouldn't think that there was some kind of intermolecular force. There actually is some kind of intermolecular force which holds the individual molecules, individual fluoroethane or methane molecules together. And all the electrons in the fluoroethane molecules, for instance, they're going to be moving around at rapid paces around the molecule, around the individual atoms. And that's going to create temporary dipoles with other molecules where the whole molecule at a very short instance, like, would be slightly delta positive on one side of the molecule and slightly delta negative on the other side. And that's going to create induced dipoles with other molecules, and that's going to temporarily bind them slightly closer together and make their attraction slightly stronger. And so as the molecules are heavier and have more electrons, that's going to mean that their binding is slightly stronger, and that's going to be harder to break apart when heat is applied. So the boiling point is higher because you have to go to a higher temperature to actually force those molecules apart and turn it into a gas, or from a solid to a liquid, for instance. So that is why, for instance, the fluoroalkane series, the boiling points get higher as you sort of go up the group, for instance. Now, in terms of each halogenoalkane with the same number of carbons, it says here that iodoethane has a boiling point of 72 degrees Celsius, whereas fluoroethane has a boiling point of minus 31.7. That's quite a large difference of temperature. To boil fluoroethane, it's already a gas at room temperature, but to boil iodoethane, you need to get to a relatively high temperature. That's quite a stark difference in molecules with the same number of carbons. That is because iodine is so much heavier than fluorine. If you look at a periodic table, you look at the number on the bottom of each of their little individual squares, that's going to be the molecule's relative atomic mass. And for fluorine, I can't remember off the top of my head, it's going to be like maybe like 15, and for iodine, it's going to maybe be like 50, 60 something. That's a whole lot more protons and neutrons for a molecule, and in a molecule, and molecules have the same number of protons as they do electrons. So that means that iodine will also have more electrons than fluorine at the same time. So within iodoethane molecules, there's going to be a lot more electrons to invoke these temporary induced dipoles than there is electrons in fluoroethane. So this is going to be so much harder to break apart and force apart by heat than fluoroethane is. I hope that makes sense to you. And there's even more trends to sort of go through. And halogenoalkanes, they also have higher boiling points compared to alkane counterparts with the same carbons. Ethane has a very low boiling point. Ethane is just HCC. Let's see if I can get this whole structure drawn within 5 seconds before it starts to disappear. Let's see. I'm on a race. No, it's got to be more than 5 seconds. But yeah, you see here, you've got ethane. That's all now disappeared. Probably, I guess they're doing a thing. I guess this is the way this little app works, is it kind of disappears the drawing once you've actually finished, which is actually quite smart, I guess. But ethane, you've seen the structure there. That's a similar structure to fluoroethane and all this stuff, but you just have an F, for instance, connected to the carbon. And as I probably don't have to draw it, that's all going to be saturated with hydrogens. But fluorine obviously weighs more as an atom, even ever so slightly, than hydrogen, because hydrogen contains a single proton and a single electron. Fluorine obviously contains more than that, and so it's going to be heavier, and so it's going to still have some temporary induced dipoles, which make it harder to break apart than ethane is. Now, none of the halogenoalkanes are particularly soluble in water. There's no real trend there. However, they are soluble in organic solvents. Organic solvents would be things like ethane or hydrocarbons, things like octane. Maybe you've got things like ethanol, ether. Halogenoalkanes are often used themselves as organic solvents. But I hope you enjoyed, and I recommend subscribing for the next videos in this series, which are going to be containing a lot of the mechanisms of reactions involving these halogen groups, these sneaky little things. But yeah, with that, I recommend subscribing for more content like this, and have a good day.